recording. Okay. All right, so I'm going to go ahead and get started. Can someone just let me know if you can see the PowerPoint?
Yep, we see it.
Okay, great. Thanks. So today we're going to be going over a new game. This new game is called Kessler. It is inspired by and very similar to the Asteroids game, Asteroid Smasher, and then Fuzzy Asteroids, the modified version that we were previously using. This one was built from scratch by us here at Thales in Cincinnati. We used some open source code similar to the Asteroid Smasher and others, but we did modify it, including modified physics and some other things. The reason we did this is because we a more stable game specifically to do reinforcement learning with. Fuzzy Asteroids had a number of deficiencies. It wasn't built for reinforcement learning. So a lot of the things that were done to it were patches and ad hoc fixes to try to get it to work. And it had problems in a number of ways. So we made this one to sort of get around those issues. And we are making this open source. It already is open source. I'll be showing you that. And just like Fuzzy Asteroids, we will be looking for contributors in the future. So, if you're interested in helping to develop games specifically for AI development with reinforcement learning, maybe you'll want to help contribute to this. So let's go ahead and dive into it. Just a reminder, we have our website. It's at xfuzzycomp.github.io/xfc. This is different from the old website, which was hosted on UC's domain. We also, if you haven't already, if you've signed up for the competition but you're not already in the Slack, please join the Slack. We put a lot of announcements in here. There's also a bunch of discussion. People ask about how to do certain things with the environment. So if you have questions about Kessler, like something down in the weeds, you can email us, but oftentimes it's a lot faster to just go to the Slack. Plus, you can see what other people have been talking about. Teams ask for help, and we respond in there such that everybody can see the answers. We also have our YouTube channel. On here, we have recordings of all of our seminars from this year. We do have some of the seminars from previous years. We also have things like the competition from last year, including the full live stream. We also have highlight videos and things like that. As a reminder, this seminar is being recorded and will be put on the YouTube channel as well for any of those that might have missed it. So let's hop right into Kessler. Like I said, it's inspired by Fuzzy Asteroids and Asteroid Smasher, written from scratch with minimal dependencies. I believe it only has 2 dependencies, NumPy and Pillow. I believe are the only 2. There might be a couple others, but very minimal. We got away from using Python Arcade, which is what Fuzzy Asteroids and Asteroid Smasher was built on. It had lots of issues, especially with things like graphics windows when you're trying to do machine learning with it. So this one was built with that in mind. So it is much faster, much more stable, doesn't have the same graphics issues. And in fact, we have a couple of new graphics options, which should look quite a bit better. One of those is tkinter, which is, I believe, included in base Python as a module with the standard library. But it's another graphics package typically used for GUIs. And then we also have a Unreal Engine 5 based graphics option that my colleague Zach Phillips worked on creating. He's maintaining that and adding new features. It's already in a really fun state, but it should get even better. So real quick, I'll just show you what the new game looks like. These are the default graphics, the tkinter graphics. You'll notice that it's somewhat similar to Fuzzy Asteroids. Right now, the asteroids in this graphics option, they're just circles. You still have splitting of the asteroids into smaller children. And then eventually the small size, if you shoot those, they disappear. One thing that we added, which I'll talk about in a minute, is different splitting behavior. And also we added momentum to the collisions. But things like the ship collisions, those are the same currently. It is just based on a radius. That's why you see this circle. We are not doing collision with the actual sprite shapes themselves, at least not yet. One reason is for speed. I would say that's the primary reason. Another reason is one of the things that we'll get to in the competition, which is developing custom ships. So we'll likely still do that. I'm talking with the other organizers right now about how we're going to implement that exactly, but we'll likely still be doing custom ships as a thing to do before the competition. But this is the general layout. You'll see all the ships in this window. This is the game. And then over here, we have details about each team and each ship on each team. The competition will still only be a 1v1, at least for right now. In the future, we may do more. Kessler can handle any number of teams and any number of ships, although performance, will suffer once you get above a certain number. But it does have the option to be extensible to that in the future if we wanted to do certain things like maybe battle royales or whatever. But for now, it has the similar functionality to Fuzzy Asteroids in that you shoot the asteroids, they split, you get a point for every asteroid that you hit, regardless of size. So hitting one of these asteroids and hitting one of these asteroids still gives you the same score increase. And the splitting behavior is still such that for each subsequent child, or well, each time you hit an asteroid, if it's not the minimum size, it will split into 3 smaller asteroids. And those asteroids do preserve momentum, and the projectiles do impact with that object, and the momentum affects the path. And that means that if you have an asteroid coming towards you and you shoot it, the momentum of the projectiles from the ship hitting the asteroid is not enough to, say, make the asteroid go away from you. You've now just split into 3, which will be coming towards you a little bit more slowly. But you'll see over here a bunch of details about each ship. It'll tell you how many lives left. We can see here that this ship already died. It has 0 lives left in this scenario. Had an accuracy of about 26%, hit 17 asteroids. And bullets left, that means how many bullets you have remaining. There may be certain scenarios where we give you limited ammo because we want to test accuracy or something like that. In this case, this says -1 because you have infinite ammo. You can just keep shooting for forever in this scenario. It's not one of the stopping criteria. But that's just sort of a high-level overview. Let's get into some more details. This is what the UE5 graphics looks like. This is held separately from the source code, so you will have to run the UE5 graphics exe outside of the environment. And then it will wait for messages from Kessler in order to show what's happening. The details for doing that are on the repo. I have the link on the next slide, so we'll talk about that too. There is some extraneous code, not just this, but a few other things like examples that are in the GitHub that are not in the wheel that you install the game with. You can still go get them from the GitHub, and you can fork the GitHub or fork that repo and do other things with it. But we are creating releases in the form of wheel files that you can install easily, which just doesn't include that. It's just the source code for the game. But regardless, this is what it looks like in UE5. We have the same border where everything wraps except for bullets, so ships and asteroids still wrap. We have these nice looking textures on the asteroids. The hitboxes are still not defined by these. They're still defined as circular, but it's very close approximation, not too far off. Looks very good. We have, glowing projectiles, a glowing wall defining the play area. It just looks quite a bit better. So it's a lot of fun to play around with. When we get to the final competition, the playoff in towards the end of March, we will most likely be using the UE5 graphics just because of how nice they look. Okay, so installation. Like I said before, it's open source. It is now, that is the wrong link. It's actually this. I'm not sure how that got put on there. Okay. So this is the repo for Kessler. It's actually on Thales's open source GitHub. And so you can go there and look at all the code. We can potentially have outside contributors. We're figuring out how to do that right now, but hopefully we can in the future. Installation, it's not currently on PyPy, although we're talking about that currently, and hopefully it will be before too long. But even though it's not on PyPy, you can install it in a similar way by just going to the releases page. And I'll just do that right now. Well, I'll do that a little bit later to show you what you would do. But you go to this releases page and you can download the wheel files with, they have the extension .whl. And there are different versions. You can grab the latest. Right now it's on version 1.1. So this is the wheel file for 1.1. That's what the file name for it. You can put that in your game directory, in your project directory, and then you can simply just pip install and then that file with that extension, and it'll go ahead and install the game like it would if you were getting it from PyPy. It's just doing it locally instead. One thing to note is that Kessler does require Python 3.10. If I remember correctly, I believe that's because of graphics. If you're running it without graphics, you may be able to run on different Python versions, but to get around that, we're simply saying that it's Python 3.10. Zach, you can correct me if I'm wrong about why it needs 3.10. Okay, so pretty simple installation. You can also just use the source code if you want. It is cleaner and easier to just install from the wheel, though. Okay, changes from Fuzzy Asteroids. It is very similar. In the repo, there is an examples directory. We're also working on making an entire example template repo for a project using it, like we had for Fuzzy Asteroids. Sam, one of the other organizers, is working on that currently, and we'll get that up for you guys. That'll be on the XFC GitHub, the XFC comp GitHub, but we'll have that up before too long. But in the meantime, there are some examples like testcontroller.py and scenario-test.py. Testcontroller.py, if you're familiar with how you do it in Fuzzy Asteroids, it's extremely similar. You are defining your controller class that inherits from a base controller class that exists in the game, and you define your actions function and your name, stuff like that. Scenario test just shows an example, and I'll show you the code for these in a little bit. Scenario test goes through, well, a test scenario. It shows you how to define a scenario, instantiate the game, run the game, get the results from the game, and how to use those. So like your scores, information about the performance during the run of that game, etc. Physics, there were a number of changes to the physics. The asteroid splits are now deterministic by default. We may change this in the future to be somewhat random, but currently it is deterministic. And so the way that the splits happen are that the momentum is preserved from the parent asteroid, and each parent asteroid splits into 3 children. One is on the same trajectory that the parent asteroid was on, with the momentum change that happens from being impacted. The 2 others occur at offset angles to the left and right of that original trajectory. Well, the modified trajectory in this case, due to the momentum from the impact. And so what that looks like is that you'll have 1 asteroid splitting off straight and then 2, 1 on either side of that. Momentum is also transferred to the asteroids from bullet and ship impacts, and it is fully elastic. Ships, you can now have more than 2 teams, although, again, the competition this year will still only be 1v1. So there will be 2 teams in each scenario, but you will only have 1 ship playing against 1 other adversarial ship. Maybe in the future we'll do something like a battle royale, but not yet. Controller structure, like I said, it's mostly the same. The inputs are now called the ship state and game state. So you have this ship state, which is a dictionary, and game state, which is a dictionary. So you have information about your own ship and then the entire game. And then the outputs, like they were previously, are thrust, turn rate, and fire. So thrust and turn rate are still floats, and fire is a Boolean. Game state data. This is what you're getting in every time step to your controller. That now consists of the states for all the asteroids that are in the game, the states for all the ships that are alive in the game, the states for all the bullets that are in the game, the map size, the simulation time, and the step size, the time step size. We may modify this as needed, but currently that is what is available in the game state itself. So this is where you would go to, say, develop all of the processing you would do to, say, let's say you wanted to assess the threat of different asteroids. Well, you could grab this list of asteroid states and go through all that information. You can see what the asteroid state information is by digging into the code, but we'll talk about them right here too. So ship state, this is available for all the ships in the game, and this includes information like is respawning, position, velocity, speed, heading, mass, radius, ID number, team, and lives remaining. And then we also have own ship state. So this is additional info that's only available about the ship being controlled. So you will only have access to this for your own ship, which includes bullets remaining, can fire, whether you can fire or not, because there is a cooldown, fire rate, thrust range, turn rate range, max speed, and drag. For asteroid state, this is what's available for each asteroid in the game. So you can get position, which is a tuple XY, velocity, another tuple of XY, size, mass, and radius. We also have bullet state, which includes position, velocity, heading, and mass. Currently, all the bullets have the same mass, which is just 1 unit in the game. I guess we're using SI, so 1 kilogram. Usage. So again, much the same as Fuzzy Asteroids and Asteroid Smasher, the scenarios are defined similarly. You have to define the asteroid and ship initial states, or there is a default behavior where if you just say the number of asteroids, it'll just put them in there randomly. Bullet limits, if any, etc. Game instantiation. So you have both normal game objects and trainer environment. The differences in these are in the settings. So trainer environment inherits from the base game, and it just sets a bunch of default settings such that it can run in machine learning situations more easily. So it does things like turns the graphics off, sets it to max, real-time multiplier, so it can run as fast as possible, stuff like that. The score class is slightly changed now. It is now based on teams. So score objects hold list of scores for each team based on the team ID. I'll show some examples of that too, but there are also examples in the example files on the repository. Scenario definition, very similar to how it was in Fuzzy Asteroids. You are defining it using a name. It's optional, but highly recommend you name it. Number of asteroids, asteroid states, ship states, game map, seed, time limit, ammo limit multiplier. Remember that for ammo limit multiplier means that if it is set to 1, you will have as many bullets as the total number of potential asteroid objects. So for instance, if you only have one size 2 asteroid, that means it can only split into 3 smaller asteroids. And so the total number of asteroids in that scenario is 4. And so if the ammo limit multiplier is set to 1, you would only have 4 bullets in that scenario. Now, each ship does get that. So if you have multiple ships, obviously, you have more bullets. But that is what you can do with ammo limit multiplier. This is useful in situations where you want to extremely limit the number of shots that you have. if you're trying to elicit certain behaviors in your AI during the reinforcement learning process. There is also a flag called stop if no ammo. This is an optional flag for stopping the entire scenario if all the ships run out of ammo, because at that point they're just going to be avoiding asteroids, and if there's only that could potentially go on forever until it times out. So scenario definition, much the same. This is an example which you'll see in the scenario test file. So in this case, we're making a scenario named test scenario. There are 10 asteroids, which we're not defining the asteroid states, the positions. So it's just going to randomly put 10 asteroids in there. The ship states, and it'll be 10 of the large size if you don't define that in asteroid states. The ship states were creating 2 ships on 2 different teams, Team 1 and Team 2. They are starting at this location, at this angle. I will note that the angle convention now is such that to the right, cardinal direction east to the right is 0. That is the 0 angle, and it is counterclockwise positive. So 90 degrees in this case is pointing up on the screen, or north, whatever you want to consider it. 3 lives. This will be the default probably for all competition scenarios, so map size, I would just leave this as default unless you're doing something very specific. Time limit, ammo limit multiplier, in this case being 0, this means that we are going to give it unlimited ammo, and stop if no ammo is false. These are the defaults, by the way, if you just don't define these. For game settings, so this is a dictionary that you pass at game instantiation, and these include things like frequency, time step, performance tracker being on or off, prints on, graphics type, this is probably the one you'll be using most often, real-time multiplier, and time limit. And so time limit typically gets set from your scenario, but settings can override that as well. Default UI, this is what that looks like. You have ships, lives remaining, accuracy, asteroids hit, shots fired, bullets remaining, controller names. These are all things that can get put into the UI, but this is the default UI settings. So the one thing I want to touch on here is the graphics type. So in this case, we're turning on the Tkinter graphics. You can also turn on Unreal with, I think it's .Unreal Engine, I think is the name of the graphics, but regardless, you can see what it is in graphics type. I'll show you in a second too in the code. So that's probably the one you'll use most often if you're setting these for when you're watching it run, not just using the trainer environment, which sets defaults for all these. And then you can instantiate a game. So you have your game settings. In this case, we're turning on the performance tracker. This just gives you information about what's happening during the game, such that you can do stuff with it outside of it. In this case, we're turning on the Unreal graphics for a graphics type, and we're saying that it's going to be run in real time because the multiplier is just 1, so that's just real time. So those are our settings. We add our scenario. So we're going to instantiate a game by calling Kessler-Game with those settings. We could also instantiate a trainer environment. It's the same thing. You're just calling trainer environment instead of Kessler-Game. And this does, max speed, no graphics or anything. So it's much, much faster for things like reinforcement learning. So then you instantiate the game object. So that's what you have here. And then you can run it. So this is an example that you'll see in scenario test, but we're running the game over that test scenario that we created. In this case, we're creating a timer. That's all this line is. And we are, in that game, using 2 controllers. In this case, we're just using the same controller, which is called test controller. And this is the one that we create in that test controller file. Again, I'll jump to the code real quick right after this. But this is how you actually run the game that you instantiated. So you can run it on a scenario with different controllers. And so what you can do is you can define a bunch of different types of scenarios, and then you can using the same game, run through a bunch of different scenarios, run through a list of scenarios, and then potentially run through multiple different types of controllers. Hint, hint. If you want to play the game against a number of different types of controllers, maybe you're going to save off a previous version of a controller that worked pretty well and you want to try to improve on that, you can play against that one. We will have a set of default ones that Sam is working on a couple of those right now for you to train against, but they will be relatively poor performing. So I highly recommend doing what's called adversarial self-play, which is where you periodically save a version of your controller, and then that is your new adversary that you try to improve on by playing against. After this runs, it returns score information. So this comes from the scoring function, which is a class, and performance data about what happened. So in this case, we are looking at the stop reason, which is part of score. We're going to look at the number of asteroids hit for each team. We're going to look at the number of deaths each team had, the accuracy that they had, and the mean eval time of the controller that they each had. So this is an example of how you would run the game and then get that information back from your fitness function. And then what you do with that is kind of up to you. You can also get information back from the scoring function per time step. The way you do that is by inheriting, basically you can create your own fitness class using the base class for score. And then you can modify the time step update. And so if you want to do something more like traditional reinforcement learning where you need time step updates or updates on the score every time step, you can do that as well. Before I jump to the code, I'm just going to show you some pseudocode. We don't currently have a training example up. We are working on that as well. But for right now, I'll just show you some pseudocode for a genetic algorithm as an example of how you would do training or reinforcement learning with Kessler. And so the high-level pseudocode would be to initialize your population. In this case, the population is the list of chromosomes that define your fuzzy systems or your AI system that is controlling your Kessler chip. Your environment settings, your scenarios, number of generations, all that stuff. You set all that stuff. And then while your stopping conditions are not met for each individual in your population, evaluate their fitness by passing that individual and the scenarios. So you're going to evaluate that individual over all the scenarios. And then you modify your population. Modifying your population, remember that's things like crossover and mutation in a genetic algorithm. This doesn't have to be the way that you do it, of course. We've already talked about that quite a bit, but you could use things like particle swarm, other gradient-free methods. You could use gradient-based, like we mentioned a minute ago. In this case, the fitness function, where you're evaluating the fitness right here, would look something like you would take in the individual and the scenarios that were defined. Your controller would be a decoding of the chromosome. So basically, you're just instantiating your controller from the chromosome of each individual. Then looping through your scenarios, getting the score for each scenario for that controller and whatever your adversary controller is. Remember that your adversary controller can be one that you get from us, even though it'll be very simple and probably easy to beat. It can also be a previous version of my controller that you've saved off. Your total score is then the cumulative score across all your scenarios, and that's what you return. So that is the fitness value that you get out for each individual in your population. And you just run that until you get satisfactory performance. So that's pseudocode for how you might do this with a genetic algorithm. Again, pretty much the same as Fuzzy Asteroids. But if anybody has any questions on doing that, please let us know. We will be creating examples that we will be putting in a separate example repository, though. And we will notify you when those are ready. So that is the overview of Kessler. I'm going to go ahead and show you some of the actual code. I'm going to have to go back to Teams real quick. Actually, sorry, please bear with me. Okay. But first, I'm going to show you the. Actually, let's go to the repository first. So this is the Kessler-Game repository. It is located here. It is public. Everybody should be able to see it. And you can go grab the code and do whatever you want. If you go to the examples, this has the 2 examples that I'll show you in a second. Currently, there's not a training example, but we are working on getting that up in the example repo. However, when you install the game, what you're actually getting is everything in the source. So everything in this directory. So this includes just the game functionality, but doesn't include the external things, like instantiating a game. So the easy way to install, like we were talking about, is to go to releases. The latest one is V110. You can see the release notes. We'll be doing this periodically as we make improvements. And what you can do is you can simply download this file, and then you just put that in your project directory where you're creating your controllers, and you can pip install this file name, and it'll install it into your environment. As always, don't forget to read the README. This talks about how to do the installation and also how to install the UE5 graphics if you want to use those. This isn't critical. You can use the tkinter graphics, which are just fine for debugging and seeing performance of your AI. If you want the flashier UE5 graphics, you can install it here, and there are a few things you need to do when running it, but again, you can ask us if you run into any issues. Documentation we're working on, it is pretty self-explanatory since everybody here should be at least somewhat familiar with Fuzzy Asteroids, but again, if there are questions, please ask until we have the documentation fully ready. But I'm going to switch over to code. So this is Kessler-Game, the actual code from the repo. So this is the source where all the things are actually defined for the game. But I'm going to go back to the test controller and scenario test. So this is what it might look like when you're developing your controller. So we're defining this class called test controller, which inherits from Kessler controller. So it doesn't matter what you call this, but you will need to inherit from Kessler controller, which is the base controller class in Kessler-Game. And then you have to define actions, this function actions. I should say a method, because it's part of this class. And actions needs to take in ship state, which is a dictionary, and game state, which is a dictionary. And it needs to return a tuple, which is a float, and a boolean, which are the thrust, the turn rate, and firing, respectively. You also need to define a property called name, and this is just a string. So it just needs to return the name of your controller. This gets used in a number of areas, and I believe it will error out if you don't define that. That should be in there. Does anybody have any questions on creating your own controller? And note that you can put other stuff in here. You can also define functions elsewhere and pull them in and use them inside of this. You may have methods in here for defining I don't know, call it data processing, and you're gonna use the game state information, and you're gonna do for asteroid in game state asteroids whatever it is, do the thing for the asteroid, and do all of your processing there, and then you can use that information in your actions. You then call your data processing function, oops, to do that data processing, stuff like that. But you do have to have this actions method defined. So let's go over to scenario test. In scenario test, again, very similar to how Fuzzy Asteroids was, but you're going to import scenario. This is a class, Kessler game and graphics type. You're also going to import your controller that you defined. In this case, we called it test controller, so that's one we're grabbing. We're defining that scenario called test scenario. We are setting our game settings. And in fact, let's go ahead and do tkinter. We are instantiating a game object using those settings, and then we're going to run that game over that test scenario with our test controller. And then we're going to use all the information we get back, the scoring information and some of the performance data information to print out certain things. So let's go ahead and actually just run this to see what it looks like with the tkinter graphics. So the one controller, by the way, all this does is spin and fire. That is all it does. Let's go ahead and run that again. So in this case, the asteroids are just defined randomly because we're just defining the number of asteroids. And all that these ships are doing is turning and firing. So you can see that when they're hitting the asteroids, they are splitting, but they are preserving momentum. So you tend to get like rings of asteroids that come out as there are really concentrated packs of asteroids. And then here we're simply printing out the results from what happened. So we can see that the stop reason was no ships, meaning no ships alive because they both got hit by asteroids 3 times. Ship 1, well, team 1 hit 31 asteroids, team 2 hit 37. So you can use this in your scoring. Maybe you want to use like the differential instead of absolute scoring. Just an idea. The number of deaths each team had. The accuracy for each team. This is a percentage, so 29, a little over 29% and almost 35%. And then mean eval time. This is the eval time for the controllers. So again, very similar to Fuzzy Asteroids, but much, much faster, more stable. So that is an overview of Kessler, where it's at right now and what you need to do to get it going. We will be making further updates, and we will be adding more examples. Let's see. Okay. The examples that we're going to be adding, one of these is in a separate repo called Kessler-Game Example on the XFC comp GitHub. And this is not ready yet, but when it is, we'll let you know, and you will have a thing showing how to instantiate games, develop controllers, similar to the ones you've already seen, but then also just like a sample training script that actually shows you how to call the game in a training script and use that in some way. How you do that will depend on what you're doing, because if you're using gradient free, or a method that uses delayed reward or cumulative reward at the end instead of incremental reward, like per time step, that'll be different. But let us know if you're running into issues or there's something you need from the game that is currently not accessible, because we can always make modifications if need be. Real quick, I'll show you the score class though, because if you are going to be doing things differently from how they are in score currently, because there is information you can get every time step, and that's what this is, the update. But there is finalize, which is the final values. And so you can inherit this score class, and you can extend this update and finalize such that you can get other information that you care about. You may want to say, do certain things with the score, besides what we're doing right here. And then you can create your fitness function by using that new score class that you have and creating the function. So, you know, whatever metrics you care about that you have held in the score class, you then combine them to get your final fitness for each individual. Not difficult to do, but if anybody has any questions about how to do that specifically, please let us know. There will be some basic examples in that new repository. All right, I think that's about it. I'd like to go ahead and open it up if anybody has any questions. All right, going once, going twice. All right, well, thanks for joining, everybody. Again, I will put this recording up on the YouTube channel so you can review it. And if you're not already on the Slack, please join. If you have questions, you can put them in there. You can email us, however you want to get a hold of us. But I recommend joining the Slack regardless, because there is some good discussion that goes on in there. Well, with that, we'll call that a wrap for today. We will be having another seminar sometime soon on additional changes for the competition, finalizing dates, things like that. Nothing has changed too much, most of it revolving around the change to the new game and how we'll have to do things related to like custom ships, things like that. But what we talked about before for the competition has not really changed. It will still be a playoff format. There will still be qualification, and we'll get those details finalized and get them over to everybody. But yeah, get out there and start training your agents in Kessler. It should be a lot faster, which is always nice. And I'm extremely interested to see what everybody comes up with. So thanks, everybody.